Welcome to what will be our absolute, totally final last video for the semester, concluding with parametric equations, for real this time. I'm excited, a little saddened, but let's get to it. First of all, let me go ahead and have a little nitpick, something that people like to worry about and get confused over. Parametric equations aren't functions. I've said as much before. I've also said it wrong before. A parametric equation is not a parametric function. It's not a function at all, right? It's a combination of two functions. If you want a function in two variables, you will have a function in two variables, just not in this class. It's going to be things like z equals x squared plus y squared. It's a function in x and y. Here, z is your single independent variable, x and y are each two different independent variables, and they combine to get z coordinates. So ordered pairs would go in, and a single value z would come out. Your end result is an ordered triple, which would be in three-dimensional space and would be a planar surface. And if you really want to break your brain over that, that's fine. Just wait until Math 2110, Calc 3, when that happens. So again, parametric equations aren't functions, just a pair of functions. And the independent variable, if you can call it that, is t. It's the parameter because it's ordered. Alright, so we got that well in hand. Great. And now to raise the issue that I had raised earlier. Is it a good idea to eliminate the parameter? As we had with the parabola cases, yeah, that was fine. You had the same curve. But when we had oscillation, maybe not so much. But here's the thing. That's one instance, right? If the equation is so simple that you can break it down, or you can reduce it via elimination of the parameter, that's fine. But here's the other issue I have with eliminating the parameter. You can't always do it. And there's a lot of weird curves that come up that we can graph now with parametric equations, one of which is the famous hypotrochoid. Hypotrochoid. A word that is difficult to say and even harder to visualize. It's given by these sets of equations where a, b, and h are all constants of your choosing. So you can pick a to be some number 5, maybe b is 3, maybe, and h is 5 or 7 or whatever you want it to be. And that all combines to be your x coordinate. And this all combines to be your y coordinate. What's that thing even look like? Before I show you, and also please note that I insist you use a graphing device on this, but before I show you, I want you to go ahead and recognize that eliminating the parameter on this is physically impossible. It just can't be done. Case in point, that's what it looks like. Right, here's my equation. I have capital R, lowercase a, and lowercase b. I use different placeholders here. There's your A, there's your B, there's your H, and I have them set to be 5, 5, and 3, and that actually gives me this nice little star. And as my variable t increases, I have W as my placeholder here because Desmos is kind of finicky about these things. You'll see that it does trace out the star pattern. That is a hypotrochoid. But here's the thing. There's so many variations on this. Let me move B around. Whoa. This is just fun. I'll move R. Maybe not. I'm not going to move R. I changed my mind on that. Like, even if you move R ever so slightly, weird things happen. I'll move A. Okay, I'm not going to. I regret that too. Actually, maybe not. Pretty cool stuff happens. Pretty cool stuff happens. Usually you have to be nice even multiples of stuff, though, for it to look nice. See, I want to get on 2. There you go. So weird, fun things happen. And that's an equation now. That's an equation we can generate. I wish you the best of luck eliminating the parameter. I wish you the best of luck plotting this by, plotting a whole bunch of points and seeing what this should look like. Just go ahead, go nuts, go crazy, have a good old time. But here's the thing. You can't eliminate the parameter. It just can't be done. And the takeaway from this I'm trying to get across to you is parametric equations are so powerful that your traditional rectangular functions, your traditional rectangular equations just can't make everything. Right? You can have any rectangular equation you want be represented in parametric form, but conversely, not so much. You can't take any parametric equation you have and magically turn it back into some rectangular equation. These things are more powerful. They can do much more. And so if you have some weird system of motions that you're trying to generate, parametric might be your way to go. In fact, the concept of the hypotrochoid stems from complex systems of motion. Let's see here. I've got actually a couple interactives from Wolfram to pull up here. Right? If you take a wheel and spin it around inside of a larger wheelbase, you trace out hypotrochoids. And depending on how big the radius of the little wheel is, or how big the radius of the big wheel is, or how far the moment arm is, how far the arm is away from the little wheel into the big wheel, all generates different hypotrochoids. And yet, not a single one of them can be made using rectangular coordinates. Just can't be done. Or if it can be done, if you come up with some trivial case, okay, maybe that one. But in general, way too much trouble. Not enough reward. And just one last thought for you. I want us to do one last thing here. I want us to sketch the graph of the plane curve made by the parametric equations x is cosine t, y is sine t. So go ahead, pause the video, plot some points, see what this thing looks like, and we'll come back. And what we should come back to is going to be cosine t, sine t. And we'll go from z, and this is a periodic, right? Cosine's periodic 2 pi, sine's periodic 2 pi, so I'll just put 2 pi here as my step. Wait a minute. That right there, that's the unit circle. This pair of equations, x equals cosine t, y equals sine t, that's the unit circle in parametric form. And double wait a minute, if you were to look all the way back to the very first week's worth of notes, you'll see on the unit circle approach, if you move t units around the unit circle, we had the x and y coordinates based on that to be defined as x equals cosine t, y equals sine t. And I asked you the question in the very first week, is that a parametric equation? Go ahead, look back to the first week. And you'll see I asked, is that a parametric equation? And now we can finally answer it. Yes. Yes, it is. That is the very first parametric equation we looked at. We started the whole semester off with parametric equations. And now we get to end the semester with parametric equations. I guess you can say we've come full circle. And as you groan with that awful pun, I bring you to the final slide. It is blank. Blank as the stairs that you're probably shooting the video right now, and that's fine. We've made it. We got through it. So I hope this has been a useful experience, a useful set of videos. I will talk more about it in person and at the evaluations to come, so I will see you then. Have a good one.